If we have a point P at some distance from a wire segment of length delta L carrying a current I, and if this distance r is large compared to delta L, doesn't appear to be from the sketch, but let's assume that it is. Okay, if r is much larger than delta L, as indicated here, then we're going to get a magnetic field at P. One more assumption, that the vector r from the segment to the point P, let's say from the middle of the segment to the point P, although if the segment is short, then any point of the segment will give us about the same result. But let's say that that vector is perpendicular to the strip of wire, so perpendicular to the direction of the current. Okay. In that case, we're going to get a magnetic field at P. And that magnetic field is going to be a result of the source, and the source is going to be I times delta L. We're going to regard I times delta L as the source of magnetic field, and it's going to be an inverse square relationship. That is, okay, the contribution of delta L to the magnetic field at B is going to be delta B. It's K prime times I delta L over R squared. Now let's compare this with the electric field, which is K times dQ over R squared. We see that the thing that goes here, which is Q or dQ, depending what we're doing with an electric field, is in this case I delta L. The rest of the law is practically the same as for the electric field. The only difference is that K prime is not the same as K. K prime has a different magnitude that we'll talk about in a minute. And also there's a direction to the magnetic field. Okay? Magnetic field will have this magnitude. It'll have a direction that's perpendicular to both I and to the vector r from the segment out to P. And by I cross P, if we do the cross product, I cross P would give us a magnetic field toward the camera in this case, because I is this way. And I said I cross P. It's I cross R. Moving I toward R with the fingers of the right hand gives us a magnetic field in this direction. So that the magnetic field at R is perpendicular to both that, to the direction of I and the direction of this R vector. In that case, we could write this in cross product notation as the magnetic field contribution delta B equals K prime times IL cross R, where IL is a vector that has a direction of the current I in the segment. Okay? And that's our source of magnetic field. Now, again, this corresponds to a situation where the R vector is perpendicular to the I delta L. K prime is 10 to the negative 7th Tesla meters per amp. And do I have an error there? No, that's right. I thought it was Tesla per amp meter. If we look at the units here, I think we see it has to be Tesla meters per amp, because if we multiply, okay, what we're going to get here is amps times meters over meters. So that's amps over meters. We want to get Tesla, so we're going to have to multiply amps over meters by Tesla meters over amps. So that's the correct unit for K prime. I think I wrote that wrong in the notes, and I'll probably have to fix that in a minute. Okay, in any case, that's value K prime, and that's the law. Now, in the event that the segment does not make a perpendicular with the radial vector r from the segment out to P, if there's an angle theta, then we have to make a correction to the law. It's the same, K prime I delta L over R squared, but we have to multiply by sine theta. We can apply this law to the case of a current loop. If we have a current loop of radius r carrying current I, then it turns out that from any point, well, from any segment along this loop, if we're trying to calculate the magnetic field at the center, the r vector from the segment out to the center will always be perpendicular to the loop. So the sine theta is always going to be the sine of 90 degrees is going to be 1. Not only that, but the current is the same in every segment. And R is the same for every segment if we're looking at the magnetic field at the center of the loop, because every point of the loop is the same distance from the center. That means that we can factor out the current I and the R squared and the K prime and just sum up the delta L's. When we sum up the delta L's around the circle, all we get is the total length around the circle, which is the circumference 2 pi r. And from that we can see that the magnetic field at the center, K prime I times L over R squared, will be K prime I times 2 pi r over R squared. And it appears to me that there's a 2 here that I didn't write down, so we should have a 2 here. And we'll get another one up here. So that, in this case, the magnetic field at the center of a loop of radius r carrying a current I is 2 K prime I over R. Calculus-based students can do some calculus and calculate magnetic fields at other points in other configurations, for currents in other configurations, for a long straight wire, for example. But they all come from this original law, which is delta B is K prime I delta L sine theta over R squared.